All right, everybody. So here goes another attempt at virtual learning and how fun it really is. Before I get into the next part of the packet, which is called Quantitative Aspects of Heat Transfer, I want to go over one of the problems that was in the packet. It was, I'm probably not reading it correctly. Actually, I have it on the computer here. I can check it for you. All right, I want to do the one where it says 31,380 joules of heat are added to water, changing the temperature from 20 degrees Celsius to 50 degrees Celsius. How many grams of water are present? Okay, let me do this problem with you guys, and hopefully we'll get it. Okay, so just as a quick review, because we haven't really done too much in this last week. All right, so we have the Q value, which is the heat, right? The mass, okay, which is always going to be grams, all right? And the delta T, that's that final temperature minus the original temperature, which is called the change in temperature. And then we have what's called the CP value, which is the specific heat capacity. I'm sorry, I'm writing really fast, so it might be a little sloppy, a little sloppier than what you're used to me writing. Okay, so Q is the heat value. That's always going to be in the unit joules. This is, I put grams mass. If the mass is going to be in grams, that's your M. Your delta T is actually T2 minus T1. So your final minus your original is how much temperature changes. And you can use degrees Celsius or Kelvin. We're probably going to use a lot of degrees Celsius here. The specific heat capacity is that thing where how much heat gets taken in and the temperature changes by a certain amount. Things like metals have a low specific heat capacity, meaning they heat up real fast, but they cool down real fast, where something like water has a higher heat capacity. The specific heat capacity has the units joules per grams degrees Celsius, or joules per grams Kelvin, whichever one you want to do. All right, so let's just figure out what this answer is before we move into some of the more, more of the intricacies. So it says 31,380 joules of heat, okay, joules, that's our Q value, are added to water, and the temperature changes from 20 degrees Celsius to 50 degrees Celsius. How many grams of water are present? All right, so the grams is what we're looking for. Right? So we're looking for the M value. And the temperature changes from 20 to 50. So 50, which is T2, minus 20, which is T1, means there's a change of 30 degrees Celsius. That's our delta T. Oh, I didn't give you the CP value. Oh, but that's because it's water and it should be all over your packet. So the CP value of water, you'll find I probably won't give that to you much. And that's because it's always the same value. It's 4.184 joules per gram degrees Celsius. What that means is you have to put 4.184 joules of heat energy into every gram of water in order to get the temperature to go up by 1 degree Celsius. So that's what I mean by when I say it has a high heat capacity. Certain metals, most of the metals are under 1 joule per gram. So that's why you put in a pan in the oven on 400 for a minute and it's going to be super hot. You put a glass of water in the oven on 400 for a minute, you take it out, and it change temperature, yeah, but it's not going to change temperature that fast. Look at how long it takes a pot of water to boil. Okay, anyway, so we got, let's plug in what we know. So Q is equal to M times delta T times CP. Well, our Q value is the 31,380 joules. So that's my Q value, right? Plug that in there. It said how many grams of water are present. Well, that is our M value. The delta T is right here, 30 degrees Celsius. And the CP value, even though I didn't give it to you, is 4.184 joules per gram degree Celsius. Okay? All right. So what happens here is, let's see, well, joules and Celsius will go away. The only thing left is grams, which happens to be a unit of mass, which is nice. Okay, so this is what we get for the next step. I'll even change colors just like I would if I was teaching you in the classroom. So we're going to have 31,380 equals, where's my answer? I already worked it out. 125.52. So we got 125.52 times m. Okay. So that's really all we're left with, right? Okay, well, simple algebra now. You just divide by 125.52 and divide by 125.52. Goes away. We have m left, and the answer is 250 grams. That's it, kids, okay? But what I want to show you today is going to be a little bit more involved, all right? So I want you to go to the page in your notes. I don't know if you printed it out or if you just kind of have your computer open and you scroll down or you keep the tab open while I'm going through it with you. It doesn't really matter to me as long as you know what you're doing, all right? But I want you to go to this page where it says quantitative aspects of heat transfer. Okay. And what I'm going to do is I'm going to set up a scenario for you. I'm going to draw it out. The spot on the left here where it says like 55 gram iron block, like, and there's stuff here, there's like empty spaces here. If you printed out your notes, you can draw it right next to that. So what I did, when I give you a hard copy, I already have the picture drawn, or I draw it with you in class, and then you kind of understand what we're doing. All right, so here's what we're going to draw. We're going to draw a 55 gram iron block at 100 degrees Celsius. So I'm going to label it, right? Let's see. I'll draw an iron block. Pretty good at drawing cubes. Okay, so this is a 55 gram block of iron at 100 degrees Celsius. So it's pretty hot, right? 100 degrees Celsius, like the boiling point of water. Stick your hand in boiling water, it's not good. Okay, then what we're gonna do is, so say we're holding this with like a pair of tongs or something. And what we're gonna do is we're gonna drop it into a cup of water. And that cup of water is gonna be at 21 degrees Celsius. So here's I'll have my cup. All right, now this is not gonna be drawn to scale. All right, so here's my cup of water. And I have 225 grams. Water, of course, is H2O. And that's at 21 degrees Celsius. So I have a scenario kind of like this. All right, I'll give you a second to draw that. Right, here's my 55 gram iron block. It's at 100 degrees Celsius. It was very hot. Holding it with tongs, and let's say that this was drawn to scale. I have a big cup of water with 225 grams of water in it, and the temperature's at 21. All right, now this is the language is important, all right? If it's at 100 and the water's at 21 currently, that means that's its T1, all right? So this is the T1 for the iron. This is the T1 for the water. Okay, now what I want you to do is we're going to draw, so we're going to drop the iron into the cup of water. All right, well, what do you think happens? Think about when you, if you have a glass of water or something, and you drop like a really hot thing, you're going to hear that tss, right? Okay, so here's what happens. Again, this isn't drawn to scale, so just kind of, do the best you can. Believe me, I am far from an artist. All right, so what I'm going to draw is I'm going to try to draw the iron block now sitting at the bottom of the cup of water. Now, if your iron is floating on top, then the laws of physics doesn't exist on your piece of paper, perhaps. Okay, but if you drop a block of iron into water, it's going to sink to the bottom. All right, now here's what happens. The notes say, this is what the notes say. The notes say that the temperatures equalize, okay? So the temperatures, I'm going to abbreviate temperatures as temps, okay? The temps equalize at, I think it's 23 degrees Celsius. I'll go back and check it, but I'm pretty sure it is. Okay. The temperatures equalize at 23 degrees Celsius. Well, think about it. That probably makes sense. The iron is really hot. I drop it into the water, which is really not, and it's cold, right? You drop it in, and what's going to happen is if I took the temperature of the water after I drop the iron in, the temperature goes up to 23 degrees Celsius. Okay. Now think about it. If the temperature of the water is 23 degrees Celsius and the iron is sitting in the water, then that must mean the temperature of the iron and the temperature of the water are both 23 degrees Celsius. So when it says they equalize at 23 degrees Celsius, what that means is this number here, this is T2 for both things, okay? It's the T2 for the iron and the T2 for the water. Okay, well, think about it, right? If you put your hand down, okay, on your desk or something, and it feels cold, what you're actually doing is you're transferring the heat from your hand into your desk or into your table or your computer desk or your whatever, your coffee table, whatever you might be touching, all right? And if you leave your hand there long enough, what's happening is where your hand is actually warming up. So your hand is losing heat to, in my case, the countertop here, right? The countertop is gaining whatever heat my hand is losing. All right, so think about that. This is what this means. This means whatever heat the iron lost, in order to bring the temperature of the water up, it has to be the exact same number. So if you go down and you're looking at your computer or you printed out your notes, which would have been a better idea if you have a printer, it says the sum of all thermal energy change in a system is always zero. All right, let me sum that up for you. This is what it means. It means we have a Q value for our iron, right? So I'm going to call that Q iron. Okay? Q iron. Now, the Q iron, the sum of all the energy change is zero. So Q iron plus Q water, they're the only two things, right? The iron and the water has to add up to zero. All right, and the question says, what is the CP of the iron block? Okay, so CP of the iron is what we're trying to find. Okay, so this is the whole question. I just wanted to draw the scenario. Obviously, if we were in the classroom, I'd be able to act this out a lot better, but hopefully you're still understanding. Most of you, when I'm teaching you in the class, you kind of get it the first time around, which is nice. But I know that this is hard because I'm not sitting there pointing to stuff over and over again. I can't see your faces, so I don't know if you're puzzled or perplexed. Okay? All right, so let's see. So we got Q iron plus Q water. All right, well, here's my question. What does Q equal? Well, if you just did the last problem with me, what you should know is that Q is equal to M times delta T times CP. Okay, but which Q? Is Q iron equal to that? Or is Q water equal to that? The answer is yes. All right, so Q iron is M times delta T times CP. And Q water is M times delta T times CP. So I could set it up kind of like this, right? All right. The Q for the iron is going to be the mass times the delta T times CP. The Q for the water, same thing. All right, well, let's go back and look at the information that was given. Now, you can go back and look on your paper too, or your computer, but if you drew the scenario here, you'll be able to see it. All right, so what do we have? Well, let's do Q iron first. Do we have the mass of the iron? We do. Okay, so the mass of the iron is 55 grams. Let's put that in. 55 grams is the mass of the iron. And remember, everyone, at this stage of the game, I'm not like going to go crazy about sig figs and all that. Okay. Well, delta T for iron, well, delta T is T2 minus T1. All right. Oh, good, I got that. Look, they equalized at 23, so this is T2 for both. So this is the T2 for the iron and the T2 for the water. All right, so for the delta T of the iron, we're going to do T2, which is 23, minus T1, which is 100. Okay, and 23 minus 100 is negative 77 degrees Celsius. Now remember, negative does not always mean less than 0, right? Negative means, in this case, the temperature dropped 77 degrees Celsius. It's important to know the difference between those two. All right, now what is the CP of the iron? We don't know, so we can call that X. I'll just call it CP for now to kind of keep everything together. All right, so there's our Q value for iron. We got the M, the delta T, we don't know the CP. All right, plus. Now we got to figure out what the Q value is for the water. All right, well, do we have the mass of the water? We do, 225 grams. Okay, let's plug that in. 225 grams. All right. God, I miss the Elmo projector because I could just point to it and you would see me writing it. All right, the delta T of the water. Well, we know the T2 is 23 for both. Okay, here's T1 for the water. So we're going to do 23, which is T2, minus 21, which was T1, and that comes out to be a whopping 2 degrees Celsius. All right. Well, again, everybody, I didn't provide you with the CP of the water, but it's understood that the CP of water is always going to be 4.184 joules per gram degrees Celsius, okay? And that's all going to add up to 0. Now, look, when I say joules per gram degrees Celsius, it's because I'm using Celsius temperatures. If I was using kelvins, it would just be joules per gram Kelvin, all right? All right, so let's see what we got. What can we cancel out? We can cancel out grams and Celsius here and grams and Celsius here. So the only things left is joules. All right. So, all right, it's time to do a little math then. But luckily for you, I already have this worked out. Okay, well here, all I can do is 55 times negative 77, right? I can't complete it because I don't know the CP. All right, so 55 times negative 77 is negative 4,235. I'm going to call it grams times degrees Celsius. And we're going to multiply that by the CP, which we don't know. All right, so we got, ready? Here we go. All right, so we got 55 times negative 77 is negative 4,235. All right, grams times Celsius times CP, which we don't know, plus. Now here, we're going to have 225 times 2 times 4.184. Well, that's good because we can complete that. And it's going to come out in joules because grams, Celsius, Celsius. So 225 times 2 times 4.184, did this a little bit earlier, is 1,882.8 joules. And that equals 0. Okay? All right. Next, which we're almost done, what I'm going to do is I'm going to subtract 1,882.8 joules from both sides, or you can add 4,235 times CP. It doesn't matter. But what's important is your CP value has to come out to be positive. You can't have a negative CP. You can't have a negative mass either. You can have a negative temperature, but not a negative mass or CP. All right, so let's do this. Let's subtract 1882.8 joules from both sides. So it's going to be a little bit small because I'm running out of room, but... All right, and what we'll do is this now completely goes away, right? All right, now we're left with, and we don't have the plus anymore because that's gone. So you got negative 4235 grams Celsius times CP equals negative 1882.8. So all we got to do now is just divide by negative 4,235 grams times degrees Celsius. It'll go away there. And we divide negative 4,235 grams times degrees Celsius. Sorry, the writing is so bad. All right. And what we're left with on this side is the only thing left is CP. That's good. CP is the only thing left. And what we're left with on the other side is negative divided by negative, which will flip positive. And the answer is 0.444 joules per gram degree Celsius. Okay? All right, kids. I know this was a little bit of a long video lesson. I apologize. That was because I wanted to go over the question before. All right, what I would like you to do is if you could try the next problem involving the aluminum dropped into water, I would really appreciate that. See if you can figure that one out for me. And then I'm going to try to do a live session this week, and maybe we'll go over the problem with the antifreeze, which is fun. All right, I hope you're all well. It's a shame that I'm not seeing all of you, and I'm getting real sick of doing this. I don't mind making the videos. I don't mind teach. I just wish I was teaching in person. I wish I was able to... Remember doing stuff? It was awesome, wasn't it? Remember, like, going somewhere? Yeah, back in the day. I miss that. All right, anyway, take care, guys. See ya.